So, in Unit 6, we're going to look at deep learning, a new method of using neural networks that's become very popular in the last 5 years. We've seen some just amazing results using deep learning networks, and you've probably seen those results, but you may not have noticed or known that they were from this sort of architecture. So, just to give you some background, here's two papers or things on some of the results of deep learning. So this first article is from the summer 2016 and talks about some applications of deep learning. Does a nice overview and a list here, but let's look at some of the examples. So one is the colorization of black and white images. So networks can be trained to take black and white images and apply color to them. These are some of the results. It's just amazing to see what they're able to do when you train these networks and this automatic colorization of black and white images. A lot of these ones we'll look at will either be based in images, and we'll look at something called convolutional neural networks for that, or in sequences of like sound, and we'll look at long-term, short-term memory networks with that. So this is adding sounds to silent movies and filling in the sounds that should be there. Another thing is automatic machine translation. Phones can now be, you can run things like Google Translate on phones so that with the camera you can just point to any, like a menu or a box, and it will automatically translate it right in front of your eyes. Object classification. So we've got these pictures and we are able to detect that the computer is trained to know that that's a car and those are mushrooms, things like that. So we can pick out jack-o'-lanterns and violet flowers and elephants, even though they're in all different poses. So it learns that. Handwriting recognition, so it's able to recognize handwriting. Automatic text generation, so we can like feed it a bunch of Shakespeare and it will learn to write its own version of Shakespeare and things like that. Automatic image captioning, so we can show it, we can train a network to describe what's in an image. So this would be a man in a black shirt playing a guitar, construction worker in orange safety vest is working. So these are descriptions of these images that the computer generated all by itself without knowing what was in the image. Automatic gameplay. So those are some of the examples of neural networks, deep learning, and what they're able to do. When you're looking for a final project, there's some really cool things in deep learning that you can do for a final project. In some ways, I wish I could do the whole course on deep learning, but we've got to look at all different techniques. So we'll look at two techniques in deep learning, but feel free in the final project to delve more deeply in any of those. So, okay, the next article here is from Nature magazine, and it's a review of deep learning from 2015 from some of the chief scientists in deep learning, well-known names in deep learning. This is a scientific paper, but it's in Nature, so it's not as technical as some, and I think it's quite accessible, and it's a great review and description of deep learning. So it talks about supervised learning and what supervised learning is. Talks a little bit about this mapping, but basically goes over neural networks with, in this case, they're trying to do 4 layers. Input units feeding to hidden units, feeding to the second layer of hidden units, feeding to some output units, and then they're trying to learn with these multi-layered neural networks and propagate the errors, back propagate the errors so that the weights change so that it can learn new material. Then it goes into this new method called convolutional neural networks, and we'll be spending quite a bit of time with this in this unit, and talking about image recognition with convolution neural networks, and describes the different ways of how you use convolution neural networks to set things up. Now this talks a little bit about training these networks. Convolution networks often have quite a few layers as they go through. Could have 20 layers. One of the challenges we saw with normal neural networks is that with backpropagation is that the errors are propagated backwards to the layers. But as you go from one layer to the other backwards, let's go up here. So adjusting these weights is relatively straightforward. So you learn and get the outputs, and you see the outputs aren't quite right, and then you use backpropagation to adjust these weights. But then when you go down to the next layer, it's harder to adjust these weights. You have less change, and then going back one layer it's even harder. So though it might work with this sort of two hidden units or 4 layers of networks, learning gets really weak down here with our traditional approach. But with a convolution neural network, we might have 20 networks. But one of the things we learned is that there are some different ways of setting up functions. One thing we'll look at is this rectifier, linear rectifier function that's going to replace our smooth non-linear curves for how we compute activations. And that's going to make it easier, that's going to learn faster, and it's going to make it easier to propagate the errors back through the networks. So this goes through convolution neural networks, talks about how they're set up, and some of the examples again of them and what they can do. Then it goes into recurrent neural networks. We'll be looking a little bit at recurrent neural networks and how they work. And we'll be looking at a certain type of recurrent neural network called the long short-term memory network. Two other quick points on this article. One is it talks about some of these well-known test data sets that were out there, and some of the progress made with these test sets. Also talks about the use of graphic processing units in PCs and how much that sped things up. A lot of the work with these neural networks is very similar to what we see in high-end games in gaming, and a lot high-end PCs often have these advanced GPU graphical cards in them that do math very fast. And what we've learned, researchers have learned, is that they're able to use that same sort of math to calculate these networks, and we can learn often 10 or 20 times faster than with a traditional computer, and run this all just on a desktop computer. So let's look at one of these neural networks. We're going to look at the convolution neural networks first. So let's look at this. This first link is probably the most important here, and it's a great explanation of convolution neural networks. Before we get into that, I'm going to look at a little bit of the visual cortex. So I'm going to open up this link here. So this is a quick overview of how the visual cortex is set up in your brain. So in the back of your brain, so here's the front of your brain, your eyes, neurons in your eyes map their outputs to the back of your brain here. And there are different visual areas here, and they're basically set up as layers that do different things. The first layer just receives the information from the eyes, and then the next layer computes some more complex, or some simple things, some more complex things. And then the next layers like 4 and 5, calculate more complicated things from these figures. So, for example, the first layer cells, just some of them will detect vertical lines, some of them will take diagonal lines, so they have these different receptors or things that they recognize. Some of them will detect moving lines and stuff like that. Now, there are a whole bunch of stacked receptors. So you have one area of this V1 that is just looking for any vertical lines anywhere in your vision system, and another section that's looking for just any sort of horizontal lines in your vision system. And in fact, there's a whole set of sequences at all different angles, and they've actually mapped out the visual cortex, and they can see that for both the right and the left eye, how it's looking for all these different sort of lines for that. And then when you move up, you start recognizing more complicated objects from those simple objects, and differentiating different objects as we go. So you have this layered approach. So that's kind of the inspiration for these convolutional neural networks. So again, what we're often looking for here is, so this is this link here, this first link, which is I think the best explanation I can find of convolutional neural networks. It's from this big data science blog. And so goes over again some of these examples. So now we can often show a computer an image, and it could say, draw a box around and say that's a person, that's a horse, that's a dog, that's a car, and that's a person over here, and identify all those objects in the image after being trained. Goes into a little of the history. Early in the 90s, researchers who were working hard at this, although not many people were doing this. There were some researchers working in different labs around the world and developing these different structures, often on the quietly, without many people being aware of it, until we saw all of a sudden these researchers were able to start winning some of the competitions for image recognition. So here's the basic structure of a convolutional neural network. You're taking an image, a fixed image, and we'll do some what are called convolutions on this. And we'll talk about what that is in just a sec. And then we'll do some what is called pooling, which will make this image and shrink it down into smaller images. Now, when we do convolution, we're going to look at different elements in this image, and we'll have different layers. So this first layer might look for vertical lines, and this next layer might look for horizontal lines, and this layer might look for some other thing. So we might have a dozen or so different features or things we're looking for in this image, and we'll try to detect them here. Pooling again shrinks the images down, and then again we do this convolution again where we look for certain features in these images. And again, we may get more features here, and then we do some pooling to shrink this down again, and then when we get to some point, we go into a traditional neural network, what's called a fully connected three-layer neural network or feed-forward neural network, where this would be our input, this would be one or two hidden layers, and this would be our output. So what we were looking at last week is basically this structure, and we're adding this all on to the beginning of it. So we have to learn what these convolution is and how we can generate multiple different features from one. And they also use this special activation function. We have to learn a little bit about that. So images are just pixels. So we take some image and we just remember the grayscale parts of it, or if it's RGB, a color image, we have the amount of red, the amount of green, and the amount of blue in that image. So we have pixel values here, and this is our convolution step. So if we have some image made up of numbers, and here we're just using zeros and ones, but these could likely be numbers like up here, where we have the numbers between 0 and 255 for the image. So this is our image here. So this would be like a black and white image since it's only zeros and ones. And then we're going to look at some feature here that's going to detect. So this is a filter that we're going to apply, and we're going to put this over. Let's see if I can scroll down. So here's showing it. Let's back up just a little bit. So we're taking this 3x3 matrix and putting it over here and calculating it. So we're multiplying 1 by 1, 0 by 0, or by 1, 1 by 1, 0 by 0. So we're putting it over this one and calculating what that's doing, and that is giving our result of 4 here. So let's see if I can explain how that's working. So let's look at applying this filter over to this image. So the first thing we're going to do is we're going to put this filter basically over this image, the top left corner of this, and then we're going to shift it over one, and then we're going to shift over one again. But let's just put it in this corner to start with. So you can see, like, if I wait, this is going through all the images, it's shifting it over each time, each time, each time. Now, this is the one, wait, come on. This is the one we're going to calculate when it's in the upper left hand corner. So if we look at, if this is our filter and this is our image, we're going to apply the image to this area here. So I can actually, while I'm working on this, just delete this area here if I want, and do that. Okay, so we're going to take this and basically lay it over just this top left corner here. So we're going to take 1 times 1, and again we're going to keep track of our sum. So we have 1 times 1 plus, so 1 times 1, and then the next one is 0 times 1, 0 times 1 plus 1 times, and there's another one here, so that's a 1 times 1. So that's what we get for the first row, and then we're going to keep going to the next row. We're going to add in a 0 times 0, 0 times 0, and we're going to go through this whole thing this way. So if we keep going, there's each one of these, 1 times 1, 0 times 1, 1 times 0, 0 times 0, 1 times 1, and write that all out. Now we can calculate that. So this is 1, 0, 1, 0, and so we end up with this calculation. So we have a 1 plus 0, and we can calculate these out. So when we figure these out, 1, 0, 1, we calculate all these out, and then we add them up, 1, 2, 3, 4, we get 4. So our result here when applying this image to the top left corner is 4. So we put a 4 here. And then we're going to shift the image over one set of cells here. So we're going to apply it here. So we're going to shift it over just one and reapply this same image to this set of cells. So again, we'd apply, we're looking at like these three. So 1 times 1, 0 times 1, 1 times 1, and then we'd go down to the next line here, that times this. So it's as if we're almost like laying this over this and multiplying the two ones that are on top of each other, and see if they're both ones, we get a 1 out of it, and we can do this sum again. So we get this calculation of this, and this is what's our convolution feature map. Now here it looks smaller than this, so we usually do some things with the edges of the image. We actually add some padding of zeros maybe around the image, so that if this is a 20 by 20 image, our convolution features will be 20 by 20. So here it looks smaller, but generally it won't be smaller when we do this for our stuff. So there are different kinds of features that we can do. This is, we just have a 1 in, doesn't do anything at all, just duplicates the image. These are some ways of doing what are called edge detection. So here we can detect any edge. We can actually have vertical line detections and horizontal line detections. We can sharpen the image, we can blur the image. There's different ways of doing things like that. So again, here they're showing a couple different features here that they're mapping here, and we're generating multiple different images. And again, note the input and the feature map are basically the same. And again, we can generate different features, because like here they have one with one diagonal line and then another diagonal line the other way, and we're generating these multiple feature maps. And again, that's done doing this method where we take this feature map, whatever it is, and it's usually a 3 by 3 matrix, and we're applying it repeatedly and shifting it through the whole image. And this is the same thing that programs like Photoshop use to apply what are called filters and things like that. So we can determine, we can fit how many filters we want uh, for how many different features we want. So we can take this, and again, that's kind of showing how we take this feature and apply it to one section of the map to get 1 pixel, and we shift it over 1 pixel, apply it again, and get another pixel in this feature map. So and again, here they're mentioning the zero padding so that image is the feature image is the same size as the original one. They talk about stride, and usually we shift the image over just one. There are times when you can shift this image over two, but we're not going to look at that too much. Now, let's look at the output function here. Now, if you remember last unit, we looked at simple feed-forward neural networks and talked about what's often called a sigmoid function. So we have activation that can be positive or negative, and then we want to get the we have inputs. The sum of all the inputs can be positive or negative depending on their positive or negative weights feeding into the neuron. And then we're going to calculate some output, the activation output of the neuron, and we want that value between 0 and 1, but we don't want it linear because linear simplifies it too much and doesn't give us what we want. So we looked at these more complicated sigmoid functions, S-shaped functions, using tangent or exponentials. Now, it turns out that there's a different kind of function that we're using often with these deep learning, particularly with these images, and that's called a rectified linear unit, or RLU. So rectified linear unit basically says anything, just ignore all the negative values. Any sort of negative value of this, if all the inputs sum up to negative, just set its output to 0. And then anything positive, just do a linear function of that. So again, we have these. It is a non-linear function in that it's linear for part, but then it breaks and goes straight a different way. And this gives us enough computation to do useful things, but also keeps it simplified so it can learn very quickly. So we'll often do this rectified linear unit here. So again, if we have an image like this where we have maybe here they're trying to show the negative values in black and the white values at positive, and we apply this image, we just get the white parts or the positive parts stay. Okay, so again, back to our, where's our whole? So we take our image, we apply our filter, and get a new feature detected image, maybe with edge detecting, and then we apply a different filter, get another one, we do a bunch of filters, and so we have a bunch of features we've detected from this image. And we're using these rectified linear units on top of that. And now we're going to do what is called pooling to shrink the image down. So let's go down here. Here's our pooling. One of the common ways we do is called max pooling. So let's look at that. So here we're going to take our image. This is a 4 by 4 image, and we're going to shrink it in half. So we're going to take every 2 by 2 section and convert it into a single pixel. Every 2 by 2 section and convert it into a single pixel. So here we're going to take this 2 by 2 section and we're going to find the maximum value, which is 6, and put it here. And now we're going to shift over 2 units and look at this whole new set, this 2 by 2, and find the max, and that's 8. Find the max here, 3. Find the max here, it's 4. So that's why it's called max pooling, because we just grab the max out of each set of cells. And this is a 2 by 2 or max filter with 2, and it shrinks the image in half. And this is a very common way of shrinking the image or pooling the image. Now there are ways of doing it with averaging and stuff like that, but researchers have found that this max pooling works best, and so they're offering using that. So again, so we have our rectified images and we're shrinking it down, and we do that to all of our feature images, so we'll have just a whole bunch of small images. So again, we'll look at our image and we'll do max pooling and shrink it down. So this is half the size of this. Now this kind of shows we could do averages or sums, or you can do max, and max just detects features differently, and so that's what, and we've seen that this works well. Okay. So this is our whole structure, and again, we might do a convolution step again and pooling a step again, and then eventually we'll take this and feed this into a traditional feed forward uh, learning network or neural network that we looked at last week. So that's where we set up. So that's our fully connected neural network. It's feed forward. We have a couple hidden units or hidden layers. We have our inputs here, and they'll feed through. And so each pixel here is connected to every pixel there. Okay, and we put this all together. We call this often the feature extraction part of the network, and then this is the classification part of the network. And then what we'll do is we'll have a whole set of images where we'll have images of boats and cats and dogs or whatever. We'll feed that through, and it will use supervised learning, saying where we already know that this is a cat or a dog, and we'll train it that way. So we'll give it an image, calculate all this up, figure out what the outputs are. Maybe it thinks this is a dog, even though it's a boat. And so then we'll use back propagation to change the weights. We'll change the weights here and all the way back through the whole network. We'll change the weights, increasing the weights that go to boat and decreasing the weights that go through dog using this complex differential equation method, which is actually not that complex once you get into it. When the code implementation is relatively simple. But that will propagate all those errors back and then show another image and see how it classifies, and then again update all the weights. And we'll keep doing this using what is called supervised learning, where we show it an image and we know what it should produce. And then we calculate some things like the error probability, how well it's doing. This talks about some ways of kind of visualizing what's happening at the different layers of this. This is a common thing where we show an image and we've trained it, and now we're testing it out. So we're showing it an image it hasn't seen before. It's detecting features. Again, we're doing convolutions. We're doing some this rectified linear units, a new convolution, rectified linear units. We're doing some pooling to shrink the images down and keep going. And then eventually we come up with some estimate of most likely this is a car, and that's the green bar over here. Truck goes this far, airplane this far, ship, horse. So it's pretty sure it's a car that's looking at. And one thing to kind of think of is that in the early layers, we're just detecting simple features like vertical lines and horizontal lines and diagonal lines and white on black and things like that. And then from that, we're building more complicated features here, and we're training to recognize more complicated features. And from that, we're actually recognizing faces or images or stuff like that. So as we go and do more pooling and recognizing, we get higher level features that look at the whole image and look at ideas like that. So here's a similar thing where we're looking at recognizing handwritten digits and how it kind of goes through with applies, and these are all the different features it's looking at, and it does some pooling, all the different features, pooling, again features and pooling, and then this is fed into our classification network as we go. Okay, so this is a pretty good article. I'd recommend reading it. I really like how it's set up. Couple other things then. The rest of this is so this is the example we'll be using in our assignment this week, actually applying convolution neural networks to different tasks. And so we'll delve more into that later on in the assignment, but we'll look at some of these examples here and look at the network, how the network is structured, and actually how it learns things. So that'll be a part of this assignment. We'll look at these convolution neural networks, and you actually will set up different types of neural networks and train them and see how they perform. There's another article here in Wikipedia that's not bad. I just love this comic. So it's just a cool thing where how hard some of this stuff has been just to tell if there's a bird in an image or not. These are just two links to examples of convolution neural networks used. Again, we talked about these inspirational ones. So here's some actual articles about how they're used for colorization or self-driving cars. I'm not going to go over these too much, but these would be, again, things you could start with if you're going to do a research paper at the end of the class on one of these examples. But for self-driving cars, they're again talking about their camera feeding into a CNN and being trained to do things. And here's their CNN. They get their inputs, they do some normalization in them, and again, they're doing some recognition, convolution, and convolution. So all these layers feeding up, and then they flatten this out. So they end up with just over 1,000 neural networks, neuron or nodes, feeding into a fully connected layer with two hidden units, one with 100 and one with 50, and the output is 10 neurons. That is what they're identifying or doing with this. So just an example of some of the uses of this. Okay, so another type of network is long short-term memory networks. So convolution neural networks are really good at fixed images or data that's not changing over time, but it has trouble with data that's changing over time. So this is a network that's become popular and is good for recognizing networks over time. It's based on this idea of recurrent networks. So here we might have inputs feeding into a layer, and that's feeding into another layer. But now we're starting to look at interconnections within these layers, these recurrent networks. Now, one way of looking at these is this breaks things up over time. So if we send inputs of our first image or our first word into this network, let's say we're doing some speech or song, so here's our first word going into this, and then we calculate some output. Now, the next time we send the second word into this network, but it also feeds its first word back into itself. So it's seeing not only its the new word, but also the previous word or what it remembers from the previous word. And then we send in the third word here, and it'll look at the third word and remember its state or what it remembers from the second word. So we kind of see this as unrolling time or processing time in different ways. And long-term, short-term networks work kind of the same way. We have this idea. Now, one of the problems we had with simple recurrent networks is just remembering things. And again, I'm not going to go over too much detail because you can read this article on this. But let's look at how these networks are set up. Now, if you remember our traditional network, so if we looked at our traditional network, it took all the inputs, multiplied them by the weights, had some sum in here, and then it often would apply like the tangent function or some sort of sigmoid function to this. So that's kind of this sort of approach. We take the inputs, and we might have the inputs from the last time we updated this network, some recurrent connections, and we apply it, sum them all up. So the inputs times the weights that they're connected through, sum them all up and go through this tangent h function to get our output. Well, long-term short-term memories are going to be more complicated like that. They're going to have this structure here, but they're going to have other structures set up through these. So they're going to do some more calculations. So at each time they'll have some memory, some state from the previous time of this network that'll go through, and they'll send that state on to the network, kind of like a miniature finite state machine built into these. And now they'll take the inputs times the weights they're connected, and then also the inputs from the previous time that are output from this. So they have those inputs too, and they feed it through this special function here that will decide how important it is. So that function will feed into this tangent h function that will calculate that and feed through. Now, depending on if we see a lot of change in our inputs, we might change the state of this network. So there's this kind of state of this network, and we're able to change that. And if we do change it, then we can use this tangent h to do some changes on this. So I'm not going to go through the details of how this works, but just realize that there's this more complicated setup in each node, each neuron has a more complicated structure that we're calculating here. And then we're going to set these up in a a network where we're just going to feed inputs into them, have this recurrent structure, and go back. Okay, so let's look at some more examples of those. So again, these sort of networks work with a series of image or of inputs that vary over time. So things like speech. So here's some information from Google's research blog talking about how they're translating phone conversations or images that they're seeing from a video camera that change over time, and using that sort of network for that. Here's another example where we're generating handwriting from this. So handwriting is something we can kind of generate with a series of strokes. So I can write something like this, have it pick a random example and then write it, and it should then write that image in different handwriting techniques using these. So it's generating those strokes, that movement over time. Music is done a lot, so there's actually some examples of music here. So there's this Google's brain team is working on a way of generating music from a neural network. And there's some different examples of generating music and music generations to this. But short-term memory networks, their main advances have been with speech recognition and understanding speech and processing speech. So, last thing I just want to mention is, so there are these standard problems that are out here, and people are competing against these, and we'll look at these in the assignments. So this is an image recognition thing where you have 60,000 images that are categorized, and you're trying to learn to categorize these images with your networks. And there's another version here, and people post their results for those. This is another example of that. Now, if you want to go on, Google has this really interesting machine learning recipes for deep learning, and they walk you through a number of these more advanced examples. So if you want to learn more about deep learning, you can do that. So now when we go to the examples, we'll be looking at convolutional neural networks and setting them up using this network, and we'll be applying them to some of these common problems that are out there. Good luck.